Hello everyone, I'm Athav Chauhan. So today I'll be taking you through two very important concepts in statistics and data science: bias theorem and probability distributions. My goal is to explain these concepts in a clear and relatable way using real world examples. You can easily connect with them. So this is our question number 2 of our series of end sem paper solution. So let's dig deep into it. We'll look first on the course overview. So here's what we are covering today. First, we'll understand the fundamentals of Bayes theorem, what it means and why it matters. Then we'll look at a simple step-by-step algorithm that helps us apply Bayes theorem practically. We'll use a real-world medical example to make everything much clearer. Finally, we'll compare three popular probability distributions: binomial, Poisson, and normal, and understand when to use each. So let's begin. Now, understanding bias theorem. Bias theorem helps us update our beliefs when we get new information. This is the foundation of modern probabilistic reasoning. For example, instead of asking what's the chance a test is positive if someone has the disease, bias help us understand a more useful question. If the test is positive, what's the chance the person actually has the disease? Pretty cool, right? This kind of reasoning is used everywhere in medicine, spam filters, fraud detection, and even in recommendation systems. Now, what's the real world applications of it? Spam detection. Email system check word patterns to decide if a mail is spam or not. Medical diagnosis. Doctors interpret test results more accurately. Recommendation system. Apps predict what you might like next. And fraud detection. Banks identify suspicious behavior. So bias isn't just a theory, it's applied daily in a real world scenario. So let's discuss the bias algorithm step by step. Now, to make bias theorem easier to apply, we use a simple five-step process. Identify prior probability. What was our belief before any new evidence? Second, identify conditional probability. How likely is the evidence if our belief is true? Third, compute total evidence. What is the overall chance of seeing this evidence? Fourth, apply bias formula. Plug in the values to get the updated probability. And fifth, interpret the results. Understand what the final probability means in real life. Now let's use this algorithm in medical example. Now, for the practical example, we are looking towards a medical diagnosis. Imagine there's a diagnostic test for flu. Here's what we know: 10% of people actually have the flu. The test is 90% accurate for detecting flu, but it also gives a false positive 5% of the time. A question is simple: if a patient tests positive, what is the actual chance that they have the flu? Now, let's compute the posterior probability now. Prior probabilities: probability for having a flu is zero point 0.1, probability for not having a flu is zero point 0.9. The conditional probability: p positive upon flu is zero point 0.9, p positive upon not flu is 0.05. So the total evidence, we calculate the overall chance of getting a positive test. P positive is equal to 0.09 plus 0.045, which is equal to 0.135. Now, the final result, we apply Bayes theorem. The probability of actually having the flu after testing positive comes out to be 66.6%. Now let's interpret the results. The result is surprising for many people. You might think 90% accuracy test should give a 90% chance of having a flu, but here's why it doesn't. First, base rate matters. Only 10% of population has the flu. So even a small false positive rate creates many false positive among healthy people. Second, false positives add up. But 90% of people don't have the disease. A 5% false positive rates create a more false alarms than true positives. Third, real world insight. There is why doctors never rely on just one test. They also look at symptoms, medical history, and other tests. Now, probability distribution in data science. Now, let's move to another important topic: probability distribution. Different kinds of data behave differently. So, we use different statistical models to represent them. Three of most commonly used distributions are binomial distribution for repeated trials with two outcomes, Poisson distribution for rare event counts, normal distribution for continuous and natural measurements. So, basically, now we are in the second part of our question number two. So, let's compare them one by one. In binomial distribution, used when we count how many successes occur in a fixed number of trials. For example, coin tosses, pass fail test, A B testing. In Poisson distribution, it is used for rare events happening over time or space. Examples: accident rates, customer arrivals, server request. Normal distribution used for continuous measurements that cluster around a mean. Example, height, exam score, natural variations. Each of these distributions play a different role depending on the situation. Now so this was our main comparison between binomial, Poisson, and normal. Let's look at the key takeaways now. The bias theorem helps us update our beliefs when new evidence arrives, a powerful tool for reasoning under certain uncertainty. The context matters. A test accuracy isn't enough. Base rates and false positives heavily impact real world outcomes. Third, choose the right distribution, binomial for success count, Poisson for rare events, normal for continuous measurements. Always check assumptions. A distribution works only when its underlying condition match your data. So yeah, that was the solution of question number two, covering both part A and part B. In part A, we have covered bias theorem. Part B, we have covered the difference between binomial, Poisson, and normal distribution.